changing?
Yes, sir. Yes, sir.
Okay, so good afternoon to all. So we are going to start this next session, that is a practical implementation of on base decisions rule on these satellite images. So let me just okay. Yes. So this is related to the satellite images that, and also I'll show you some kind of this Python code to implement this same code, same based rule on this iris dataset also. Now let me start with this. So these data sets on the satellite images of Kolkata. So you are given with 4 different images, as you can see. So it was taken from this Professor C. Murthy lab, ISI Kolkata, during my tenure in ISI Kolkata during my PhD time when I visited ISI Kolkata. At that time, we implemented it. That is this satellite images of Kolkata. That is 4 different images will be given to you. One is called this red band image, and each image will size is called 512 into 512. I mean, you are given with these equals size images. So if you can see these images, this image that is a Hooghly River. Because I think all of you visited Calcutta, then you can see there's a Howrah Bridge, and below Howrah Bridge one river is flowing, and this river is called the Hooghly River, and this river is this river, as you can see here. Okay, so and this is called a and we are trying to apply base decisions rule to classify these 2 region of this image. One is called the river region. As we can see, this is called a let me take as you can see, this is called a river region, as you can see, and this is entire area is called the river region, and this is called this non-river region, or you can say the land covered area. So there are many places, I mean there are many things are there in this land covered area, and this objective is that you are given with a 4-dimensional feature vector. That is, one is red band image, another is G band image, another is B band image, and another one is I band image. Means total 4-dimensional feature vector is given to you. So each image will have the same image size. The image size is same for both the, I mean the image size is equal. So it means that when I say this image size is equal, then we'll say let me just draw. Suppose this is a image. It is nothing but a 2-dimensional array. So I can define this is a matrix. This is a 2D matrix. It has got m cross n. As I can write, this is m cross n. So this is m rows and n columns. So this is a, I can say this is an image. I is an image with dimension. We can have this m cross n. That is a defined as, that is a 2-dimensional matrix. The image is, it is a nothing but it is a 2D matrix. Okay, which m you have this. This is, you can have that is a, you can have this column and rows that you can define. Now this each image size is 512 into 512, means you have m is equal to 512 as that I can write. This is a 512, and n is also, that is a 512. Okay, so this is a image. So you are given with these 4 images. So means you are given with this 4-dimension feature vector. Means if you are going to make a feature vector, so this is a first feature vector. You can have, it is an R band. This is an R. This is a second feature vector, that is, you can have G band. Then you are going to have third feature vector that you can have, that is a B band, and fourth feature vector that you can have, that is a I band. So you are given with this 4-dimensional feature vector. So this is an each image, and each feature vector is an image. That is a RGBI. So this is the input data is given to you. That is a R band, G band, B band, and I band. And this, what is your objective? You have to apply this base decision rule, and how to implement it, that I'll explain to you. Then after understanding that, you can ask many questions, and then you can try by yourself that to implement it, and you'll definitely get the results, very good results. That the result that I'm showing here, that output image, that after applying it, you can get this output image should be like that. Okay, so we have started with this same image size 512 into 512, and these things also you can also get this 512 into 512 these images. So total, how many images that you are going to get? I am going to get 3 different images, output image. So this output image, this is called the river class. Now the river class, it is entirely white, and this non-river class or land covered area, this is completely black, dark. So this is a gray level, grayscale images. So this is a with intensity where this is 0 and 1, or 0 and 255, I would say. So 255 is completely white, and 0 means this is a completely dark. So with this is a P1. P1 is given, and P2. So what is P1, P2? P1, P2 for your prior probability for the river class. This is called the river class. So this is prior probability for that you can write for the river class, and this P2 means that is a prior probability for, this is a non-river class. So that this is called this non-river class, so that you can write this is a non-river class. So this two information, then we can apply Bayes rule, and that you can get the result. So now here, when I'm going to apply Bayes rule for P1 is equal to 0.7 and P2 is equal to 0.3. Okay. Then you are going to get another result. Now you can just look at, there is some dotted pixels. Actually, it is if you just see my previous lecture, so there is some error. I mean, the probability of misclassification error. Now it is actually belong to class 1, means river class, but it is classified in non-river class. So this is an error. So similarly, you can have this P1 is equal to 0.5 and P2 is equal to 0.5. So finally, you can get these 4 different images you can get. Now, how to implement it? So this is implementation steps. Suppose 4 satellite images of Kolkata that is given, and you can see that is 4 satellite images, R band, G band, B band, I band, and each will have this equal image size, that is 512 into 512. Okay, and this dimension of the feature vector is 4. So means, so dimension of the feature vector is 4 means each pixel location you have how many value? 4 different values. Okay, now let me explain this. Each pixel locations you have 4 different values. Suppose this is your image. Okay, and suppose this is just this is a intensity values. So suppose this is the image. Okay, now this is an x comma, this is x comma y. that you can have. This is x, y. Now, this is what should be the location. This is 1, 1. Okay, this is 1, 2. Okay, so it is suppose 1, 3, and this is 1, 4. So if I'm going to have, this is a 1, 2, 3, 4, 4 cross 4. My x is 4 and y is 4, kind of things. 4 cross 4 image is, if it is given. So this is my pixel location. And each pixel location you will have 4 different values. So this is the image, and this is my feature vector. The image, from the image you are going to have this feature vector. Now for each pixel location, how many feature values you are going to get? 4 different feature values. From where you are going to get 4 different feature values? Because for 1, 1 location, suppose this image size is same. For 1, 1, this location, when you are going to read it, 1, 1. So how many pixel values? So you are going to get 4 different pixel values for 1, 1. Okay, for 1, 1 pixel location, you can get this R-band value. So this is a R-band values. This is a G-band values. This is a B-band values. And this is I-band values. For each pixel location, you can get this 4 different values. For 1, 1 location, you can get 4 different values. For 1, 2, you can also get these 4 different values. For 1, 3, you can also get the 4 different values. So that's why each pixel location you have 4 different values. So total you are going to have 500 into 512. Then this dimension will be your 4 into 512 into 512. But each pixel location you have 4 different values. Now 2 classes are given to you. You are going to have these 2 classes, river and non-river. Now you have to take training sample points. So 50 sample points. So 50 sample points from river class for training of for each band. Now whenever I'm going to have the sample points, so you are not going to have the intensity value. So now what is the difference between intensity values and pixel location? So whenever I'm going to have the each location, so each location means XY coordinate, spatial coordinate, I'm telling. Okay, XY coordinate. And for each location, you have 4 different values. So values means intensity values. Okay, so this intensity values, it is a nothing but it is a grayscale value. If you are going to use 8-bit images, now this intensity values will be 2 to the power 8 minus 256. So 0 to 255. I mean these all the pixel. I mean all the locations you will have the pixel intensity value in the range of 0 to 255. So this way that you can understand. So whenever I'm going to have the take 50 sample points, okay, means you are going to take the 50 pixel location, not the intensity value from the river class. Now how are you going to choose it? That I will tell you. And take 100 sample points, means pixel location, from these non-river classes for training for each value. So you are going to take 50 samples, training sample points from river class, and that will repeat for the each band. So why it will repeat? Because each image size is same. 512 into 512 means whatever pixel location you are going to select, so that locations will be reflected for these other images also. Okay, now that will be more clear when I'll just explain further. Now, so first you have to do this training data points for 50 sample points for river class, and you can take the 100 sample points for this non-river class. You may also take more than 50 also, more than 50 and more than 100 also, no problem. Now, by using the training samples points, you have to train this model based rule and other thing. Then you have to test. Whenever you are going to test it, for your test image should be the total image. Why total image? Because ultimately you have to start with this input image is 512 into 512, and this image that you are going to display, that also you are going to display by 512 into 512. Now take 512 into 512 sample points, means you are going to take the pixel locations. Okay, and for each 512 into 512 image, each within this sample points 512 into 512, each pixel locations, you can get the 4 different values for the test image. So that you have to check it. So this image, whenever you are going to use for testing, and if I am going to pick up the first one, then also apply the Bayes rule. Then when the model is trained, then accordingly you can get the answer. So you'll also see. Now you have to apply this Bayes decisions rule to classify all the test sample to check whether the test sample belongs to a river class or test samples belongs to non-river class. Now from the 512 into 512 image, whenever you are going to using as a test samples, this is a 512 into 512, 512 into 512. So this is your test samples. This test sample image that you are going to choose. So now, for each pixel locations, you have to check whether what is the class belongingness of the point. Now, if it is belong to river class, then these pixel locations will set to be 255. Now, if this pixel location does not belong to the river class, then these locations will be 0. Suppose if you take the 1 1, now you have to check 1 1 is belong to river class or it is a non-river class. Based on this density function or the likelihood function that you have already calculated for this Bayes decision rule. Okay. Now, if it is not belong to river class, then put it as a non-river class. And if it belongs to non-river class, then this location, the intensity values, make it 0. Okay, or make it 255 based on this class belongingness of this pattern. Now you have to show the results in image in the black and white images like the 0 and 5. So this is this implementation. Now how to implement it? So how I am going to apply the same example that I will also extend for your k-nearest neighbor also. Then you will see these differences of the Bayes decisions rules and this k-nearest neighbor. So now how to choose it? How to choose these sample points? Now here, as you can see, that is the important things that this is a river class. Okay, as you can see, this is a river class and this is a non-river class. Now, as I already told you, you have to choose the sample points, means pixel coordinate positions. As you can see here, this is x coordinate river and y coordinate river. Okay, from the xy. So this thing. So you have to choose the sample points from the river class in such a way so that the overall variability of the classes has to be maintained. So what is the meaning of the overall variability? Now, instead of choosing this entire region of the river class for these training data points, if I'm going to choose only from here, only from this region to this, okay, only this here. So obviously it will affect my classification as well. How? Because your actual mean, if I'm going to take all the training data points from the entire region, my actual mean will be somewhat like that. Yes or no? Okay, my actual mean would be somewhat like that. But if I'm going to take the training data points only from this region, then my mean will be here. Okay, then this actual mean, okay, is deviating from my this mean. Okay, so there is a problem of this. There is a shifting of the mean. If there is a shifting of the mean, then obviously there is a problem in the covariance matrix also. If there is a problem in the covariance matrix, then it will also affect the inverse. So all the things will come. Okay, that's why. So whenever you are going to use the training data points, so training data points has to be chosen in such a way so that it will preserve this distribution. So okay, so this distribution that should be in this the mean should be, you have to choose, so the overall variability of these classes has to be preserved. So you have to choose this good distribution. For these things that you have to check this mean, actual mean, what is the actual mean, whether this actual mean will represent this entire population of this data set or not. So that we need to take care of it. Okay, similarly for this non-river class also, we need to take the features from here, we need to take these features from here, otherwise there will be a problem in this case. So now I am going to choose this x coordinate river. This is not intensity value. So here this is called your this is a this you are going to get an image. How many points you are going to choose for the 50? Now what is the size of the feature vector? I am going to get this size of the feature vector is for the river class 50 into 4. So this is my river class forward. Now what will be the feature size of the feature vector for my non-river class? It should be 100. It should be 100 into 4. Why 100 into 4? Because this is my R2. This is my non-river class. Okay, as you can see, so this way that I can choose, that is a river class, and that I can choose, that is a non-river class. So as you can see here itself, that is a 50 points, 50 training points of pixel coordinate. Now each locations, for each location 1, 5, 4 and 19, so this is one location, I can get 4 different values. I can get 4 different values. So these different values that I can write, that is for R-band image, this is for G-band image, this is for B-band image. I mean I can write in this way also. This is R-band image, this is okay. So I can get for R, G, B and I. Okay, so this 50 into 4 means I am going to get 50 sample points, and for these each images. So similarly, I am going to get this 100 sample points for this each image, each band. So this way that you have to calculate it. Now this is a base rule that I already explained you. That is you have to here C is equal to 2. So the classes are given here, C is equal to 2, and you have to calculate. Now I need to calculate this. I need to calculate P1x and P2x. I need to calculate only. So it is nothing but that is a P1 P of x given W1, or I can simply calculate probability of, I need to calculate probability of x given omega 1. So that I need to calculate, and I need to calculate probability of x given omega 2. So these two likelihood function of x with respect to this class that I need to calculate PHW and PHW2. And finally, you can put x in the class I if this condition is satisfied. Okay, now let's see how to implement it. And for these things, I need to I also explained you that you need to apply this P of x. Okay, so what is the density function? We are going to use multivariate Gaussian. So that is nothing but 1 by root over so I can write 1 by root over 2 pi to the power m. This is 2 pi to the power m. M is a dimension of the feature vector. Determinant of sigma to the power half. Determinant of sigma to the power half means square root. Then exp of, then you have to have exp of minus half. Then x minus mu. X is a vector, mu is also vector, that is prime, that is a sigma inverse. Then x minus mu. Okay, so this is things that you need to calculate. So 1 by root over 2 by to the power n, determinant of sigma to the power half. So I need to calculate for x minus mu transpose, this entire expression that I need to calculate. Now how to calculate it? Then after that, after calculation it, if you are going to find, so this is this base decisions rule that maximize this probability of misclassification. Now we'll see how to implement it. Now implementation process of the density function. Now you see that calculate this mean of the river class. So first you have to calculate this mean of this river class. Okay. Now this mean of the river class that I need to calculate. So now you have two class. One is called this omega 1. Omega 1. Omega 1 is your river class. I am going to write RC. And you have omega 2 also. Omega 2 is your NRC, non-river class. So you are going to have two class. Omega 1 is the river class and omega 2 is your non-river class. Okay. And this you have to how to calculate this mean. So mean will be T1 is equal to mean of. So what is the formula for mean that we have already seen? We can calculate that is a x bar is equal to 1 by n. Okay, 1 by n summation of that I is equal to 1 by n into xi. Okay. Now what is the value of n here? Because here n is 50. So what you have to do? You have to calculate x bar is equal to 1 by 50. I is equal to 1 by 50 into, that is a x1 plus x2 plus x2. So these are the intensity values that you can calculate. So there is a mean of these urban images. Okay. So you can get the first mean. Okay. So I can have, instead of writing this x, I can write it is a mu. Okay, I can write it is a, you can write this is a mu. Okay, so it is a vector. So because whenever I'm going to use a vector, you can calculate, that is calculate mu1. You can calculate mu1 for mean for the red band image. Then mu2 you can calculate, that is a mean, mu2 is equal to mean of green band images of 50 sample. Then you can have this mu3 for, that is, and mu4. So total 4 mean. How many mean you are going to have? That is a, this is a mean vector is, it is a column, it is a column vector 4 cross 1. So you have a mean vector. Suppose this, you have a mean vector is dimension by, that is a 4 cross 1. Why 4 cross 1? So you have a mu1, you can write mu2, okay, you can write mu3, and you can write mu4. Clear? So mu1 is a your red band image, mu2 is your for green band, mu3 is a blue band, and mu4 is a infrared band. So similarly, you can calculate this mean of this non-river class also. Okay. So same formula you can apply it. The same formula. Only you have to change this n. Where we are using this n is equal to 50 for the river class. Here we are going to use this mean is equal to n is equal to 100 for this non-river class. So you, this way that you can calculate it. So mean of G band images are 100 points. So here also you can calculate this mean. Okay, like the mean that here also you have calculated. This is a mean of all those things. Yeah, this is a mean of for all those things. So mu1, mu2, mu3, mu4. Similarly, also mu1, mu3, mu3, mu4. Now next is you have to calculate this covariance matrix for this river class. So now you need to find out, that is a, you need to find out, this is a covariance matrix. Okay, so how to find this covariance matrix? So I already explained to you. So this covariance matrix, what you're going to use? So So for this, you have to calculate this covariance matrix for the river class for 50 sample points, that is 4 into 4 dimension. So what is the size of the covariance matrix? So that will be your 4 cross 4. That covariance matrix size will be your 4 cross 4. Okay. So yeah, what you have to do? You have to calculate covariance matrix of COV of R band into R band. Okay. Then you have to calculate covariance matrix for R band into G band. COV of R into G band. Next, you have to calculate this COV of, so I need to extend it, COV of R band into B band, then R band into I band. So similarly, here also you can calculate it. Okay, and finally you can have, that is a COV of, okay, what I should write? I band into R band. Okay, then COV of I band into B band, then finally COV of I band into green band, then final you can have COV of I band into I band. So this you can get total. How many elements you are going to have? You are going to have total 16, 4 cross 4. So this is the size of this covariance matrix, and you are simply using this formula of this as I already told you, this covariance matrix for formula COV of x comma y. What was the formula that we have already studied in the previous lecture? COV of x comma y is equal to 1 by n. What was the formula? The summation of, okay, what I mean, xi minus x bar multiply by yi minus y bar. So that we have already understood this concept, where I is equal to 1 to n. So this formula we have already seen. Here also we have seen the deviation. As you can see, x minus t, as you can see here also, x minus t1 deviation into y minus t. I mean, how these differences is there? So t1 is nothing but, what is the t1 and here the mean? This is a mean. So this is actually a mean, xi minus x bar into yi minus. So this is a xi minus x bar. This is a, you are trying to extract the value from the mean for this river class, and this yi minus, this is a non-river class. So you calculate this covariance matrix for 50 sample points, which is 4 cross 4 dimension, basically x minus t deviation into y minus t, and multiply it and summing them up. So as we have already understand, where x and y represent these sample points for training RGBI, and we will get this 2 to the power 4 16 values for the covariance matrix for, different possible combination. So what are the different possible combinations? I already explained here. COV of R comma R, you have to calculate, apply this formula, COV R comma G. So total 16 values you can get. Next, we have to calculate this covariance matrix for non-river class. So you have to calculate, because you're going to solve this 2-class classification. So you need to estimate this covariance matrix for first class, omega 1, and covariance matrix for this omega 2. Omega 1 is a river class, omega 2 is a non-river class. Now for your non-river class, this is same thing, same procedure you need to apply. 4 cross 4 dimension also you can get, because here already data points are large than this, but this dimension will be same. Total 16 points will be there in the covariance matrix. All the diagonal elements are nothing but a variance. So all the diagonal elements are also nothing but a variance for this river class. And so this is for the river class. You can get this covariance matrix that you can get for this omega 1 as well as you can get for omega 2 for both the classes. So you need to calculate this omega 1 and omega 2 for both the classes you need to calculate. So now take this whole image for the test data. Now, what is your test data size? R-band image, G-band image, I-band image, and B-band image, and you have to make a loop from I is equal to 1 to 512 and Z is equal to 1 to 512, obviously because this test image size is also same. Okay, and test data, it is nothing but a coordinate positions, as I already told you. So in the training data points, you are just picking these few sample points. You are taking these few sample points from this river region, and you are taking these few sample points from the non-river region. But whenever you are going to test it, during testing, you are taking this entire images. As the entire image size is 512 into 512, then you have to make a loop from I is equal to 1 to 512, Z is equal to 1 to 512, and the dimension of this test data is 4 into 512 into 512. So that is a very, well acceptable. Now, for each pixel location of test image, okay, now you have to check. You have to check for each pixel location, as I already told you, what is the class belongingness of these intensity values corresponding to their pixel location, okay, by applying the base rule. If it belongs to the omega 1, then make it 255, that is a river class. If it belongs to the omega 2, that is corresponding to non-river class, make it 0. So now for each pixel location, you have to make a loop from I is equal to 1 to 512 into 512. Now for the river class, what you have to do, you have to calculate this test data minus T1 deviation and test data minus T1T. Okay. And this portion, it is nothing but the formula of the multivariate Gaussian. Actually, it is very difficult to write this. So there is an inbuilt function is there in Python that I'll show you. That is you can easily call it and you can get the answer. But actually, what is going on? So you need to also understand. So the formula multivariate Gaussian. If you just recall the exponential term exp of minus half x minus mu, what we are written in the multivariate Gaussian, there is an exponential term now in minus half. Then as you can see, that is a x minus mu transpose sigma inverse. Okay, then x minus mu. So that was there. So here also test data means x. X is your test data, and T1 means that is a mean. So, and deviation and test data minus T1, that these things. So that we are going to write. That is a transpose. So as you can see here, also written test data minus T1 and test data minus T1 transpose, then multiplied. Now for the river class, you are going to calculate what you are going to calculate test data minus T1 into inverse of covariance matrix of the river class. Okay, because you have already calculated covariance matrix of the river class sigma you have already calculated, then you need to calculate sigma inverse. So you have calculated covariance matrix for both the classes, RC and that is a covariance matrix for river class, and NRC covariance matrix for this non-river class. Now inverse it into test data. So it is just this part exponential of this whole thing that you have already calculated from this step. Now similarly for this non-river class, you calculate this test data minus 2. Okay, this test data minus 2 and test data minus, T2, not 2. This test data minus T2. So what is T2? So T2 means that is a mean vector for this non-river class. So you have calculated this mean vector for river class, and also you have calculated this mean vector for this non-river class. Now here also this test data minus T2, that is a test data minus T2 for, that is a for this non-river class. Okay, that if you just go back, you can say T2 means here calculate this mean of the non-river class, so T2, and T1 means calculate this mean of the river class. So then here also you can just use the same formula, non-river class test data minus T2 transpose into covariance matrix of non-river class. As I already told you, here also you need to calculate this covariance matrix. Okay, one covariance matrix for this non-river class, multiply by, there is a test data minus again T2. So we are just applying this formula. Okay, x minus mu transpose multiplied by sigma inverse. So this formula that I am going to apply for calculating this density of the river class as well as this non-river class. Now in the step 10, so what you have to do? You have to calculate the density function. Now here, what is the density function? That is a density function P1 for river class. You have to calculate with the prior probability for the river class is 0.3. Given how we are going to calculate this prior probability, so that I already explained. Now how we are going to calculate the density function? 1 by determinant of sigma to the power half. Half means square root. Now we are not going to write 1 by root over. We are not going to write 1 by root over 2 pi to the power m. Why we are not going to write? Where m is here, what is the value of m? M is 2. So because 1 by root over 2 pi to the power m, this is a constant term and this is same for both the classes. If this is same for both the classes, we can cancel out the term. So that's why we are not going to write it. So we are starting this P1 is equal to 1 by square root of determinant of, you can see determinant of covariance matrix or matrix. Okay, so this is a nothing but 1 by root over 2 pi to the power n. We are not going to write. We are going to write only this determinant of sigma to the power half. So determinant of sigma to the power half. So it is a, this is a square root of these things that I have already explained. Multiply by exp of minus half. So there was a formula of 1 by root over 2 pi to the power m determinant of sigma to the power half exp of minus half. So minus half is 0.5 into, that is a river class. We are applying this multivariate version. So this the river class means you have already calculated this component for this river class. You have already computed. Okay, I'm just going to add it for minus half was not there. So I'm going to write minus 0.5 into river. You just see the test data minus T1 test data minus T1 into transpose inverse of covariance matrix in river class. We have, so this value you have already obtained. So you have already obtained these values. You have already obtained these values. Okay, for this river class and this non-river class. And this apply this multivariate normal, and you have to calculate this density function P2 for this non-river class also. For this non-river class also, you have also calculated this P2, where P2 is equal to 0.7. Okay, because you need to give 3 different cases. What was the cases? The prior probability P1 for the first class, that is 0.2. Prior probability for the second class is 0.7, or prior probability for the first class is 0.7, prior probability for the second class 0.3, vice versa. Okay, and this is a P2 is given. Now you have to calculate this density function for this non-river class, that is the square root 1 by. So 1 by root over 2 pi to the power m will be cancelled out for river class, and the non-river class is a constant term. 1 by square root of determinant of covariance matrix means determinant of sigma. So determinant of sigma to the half means square root of these things, and exp of minus 0.5 into non-river class. Okay, so you have calculated this density function P1x and density function for P2x. So you have calculated this density function P1x. You have calculated this density function for P1x, and you have also calculated this density function for P2x. Both the density function you have calculated, And next step, for each pixel location, because you are making a loop. Now you just check. You just check step number 7. You are making a loop for is equal to 1 to 512 to 512. So that many times that you have to run the loop. And for each pixel location of test image, you have to apply the base rule, that is P1 into P1. Okay. Now I'm going to apply this base rule, that is a capital P1 X. So this same base rule, that is a capital P1 X, or I can write capital P1 into small P1 X is greater than is equal to capital P2 into small P2 X. Okay. Now for each pixel location, then you are having this total 512 to 512. Now you have tested for one pixel location. Now you have to make a loop for that many locations, and finally this output image will be printed as, that is a, if this output image, if this condition is satisfying, then if this density with this prior property is greater than density with prior property with other class, then put it in, make it another output image is 255, that is the river class, or else you can make another output image 0, that is for the non-river class. Then you have to again go to step 7. Okay, so it is a repetitive way that you are going to do. Now you have to show the 3 output image using this IM show function for these 3 different cases. Now if you are just changing these prior probabilities for 3 different cases, you can generate the 3 different images which I already shown in the first class. Okay, so finally you can get this out. So but here there is some problem. Those pixels who are actually belong to things, so there is some error. So you need to again calculate this, I mean, the probability of the misclassification error, and also you can remove this error. Also, it will also give it to you for a better classification accuracy. You can also reduce this error, and for the reducing this error, you can do some pre-processing, or you can do some dimension reduction technique. Okay, and then finally you can improve this classification accuracy. So this is a simple steps of how to implement a base classifications rule on the satellite images. So now if you just do it for I mean satellite images, so this is an so before implementing on this KNN, so I just tell you that is a other way. So I can show you this code. So can you see this screen? So you can check that that is a base rule on the satellite images that you can check. Okay, so let me just can you see the screen? I think. Okay, so let me just share again. So you can just check that. As I already told you that you have to take these satellite images. This you can just process these satellite images and you can just use it. So now these are this code that you can just check it on. You can just you take some time. I'm giving this 10 minutes time. You can just write down this code which I have written, and you should use the Jupyter notebook. And you can import these libraries. So I'm just making little bit of larger so that you can able to see. Okay. So here we are just importing this different library. Import NumPy as NP, import pandas as PD, then sklearn this data set. These are the standard formula, I think you know, and you have to import this load iris, these data sets, and we have to use this model. Okay, trend test split. Then we have to use this classification report. For these things, we have to use this sklearn dot matrix import classification report and accuracy score. And here also we are going to write from stats some multivariate normal that we are going. We need to import different libraries, and in order to import these different libraries, so you need to use this standard syntax. Okay. Now you see in this first step, because I'm not going to run it now because I already run it. And first step one, I have just written step one because the PPT which I have shared already with you, you can just check that how these things can be implemented. So if you just see for this, so there are three classes, Setosa, Versicolor, and Virginica. So there are 4 different features, and each feature size, I mean, each class will have this 50 samples point. And that is total number of is 150. So total 4 features is there. Now you need to apply this formula. So first you need to load the data set. That is a comment. Then split into training and test set. Then extract features and label. So we're just using the same way. So train test split, load this iris data and train test split. Okay. Then you have to estimate this class prior and likelihood. So for the train test, load iris data, then it's data, that is features. This is sepal length and the petal measurement, or you can choose both. Okay, all other things. And then there's a target class. You need to make a target class. That is a target class level. That is Y. X is the features. Y is a class level. Then it is 0. It is a Setosa. I mean class 1, omega 1. 1. That is a versicolor. That is omega 2. And there is a Virginica. That is a I mean third class. And this class names that is giving iris dot target names. Now we have to split the data into train test split, that X train, X test, Y train, Y test. So these are the common way that you know that we need to follow it. And next we have to estimate the class prior and the likelihood. So as you can see here, so for each class we need to compute this prior probability, compute this mean of features, and compute this covariance matrix. And we are going to assume that each class will follow this multivariate Gaussian distribution. And step things that we need to for each test samples we need to compute the likelihood and posterior. Now we'll see how this can be calculated. So for this, we have to estimate this class prior and the likelihood function. So that is a priors, and so we need to calculate this prior, then mean, and this covariance. So mean vector for each class, covariance matrix for each class, and this is a prior probability. Now for C classes, so we have to calculate these priors. So here this prior probability, that if it is not given, that you can n1 by n this formula, that by using you can use it. Means there's a np dot mean. Okay, so mean of the features for class you can calculate. Covariance matrix you can simply use. There is no need to write this formula the way that I was explaining to you. There's a covariance matrix of C np dot cov and this xc, okay, into rho var is equal to false. I mean this is a syntax that we have to use. Now step 4, base decision classifier. Then this is a prediction. Why predict? Now for all x in x, so we have to calculate this posterior probability. Now for C in X, so I am going to calculate, this is a likelihood function. So this is a multivariate normal PDF probability. PDF means probability density function. X mean is equal to that you have already calculated at covariance matrix. So you are giving this parameter. So what is this parameter you are going to give? So the parameter that you are going to give, it is a mean and covariance matrix. Okay, and posterior is equal to, that is a likelihood into prior, because you are not going to use the denominator part, because this denominator is same for all the classes. This denominator will same for all the classes, and that's why we are only considering this a likelihood into prior, and then you can append it, this posterior dot append, and then you do this prediction, y prediction dot append np dot argmax for posterior. Now you have to choose class. We have to choose class based on this maximum, I mean posterior value. Which one will give it to this maximum posterior probability value? So that I mean class, I mean this test sample will classify in this particular class. Now then finally this y has been predicted. Then you just return this np.array.y predicted. Now this make predictions. Now y predicted means base classification on this particular X cluster. Now you have to do some performance evaluation. So there's a classification report. There's a accuracy y test into in the comma y predict multiply by 100. Okay, and this classification report that you can have, this is a, if you just use the classification report, you can automatically calculate this precision recall and F1 score. As this data set is very good refined data set, and we are going to use 70-30, so we can get this 100% accuracy in this case. So this is a simple technique to use it. So you need to first install it, and in the backend, so there is a code is running, okay, in this case, and then you can connect to this all the Jupyter notebook in your case, and those who are already acquainted with, so I think no need to explain all these things, these Python packages, how to import it, and how to install it. So this is my home page. As you can see here, all the PPTs, and I mean this Python file is already available over here, and I can easily I mean use it for this further application also. So thank you so much for this session. So if you have any questions for these things, you can just ask me for this base decisions rule, and I'll take a short break, 5 minutes, then I'll start this k-nearest neighbor rule. Thank you, sir.
Yes, sir. Yes, sir. So next session that we will start after 5 minutes. Is it okay, sir?
Yes, sir. So I'll take just for 5 minutes break, then I'll start this next session. By the meantime, I'm sharing this PPT so that you can share these participants also.
Okay. Okay.
If they are interested, so they can just try to implement it. Okay, sir.
Yes.